there. You know when you write a piece of code that calls itself and you just kind of step back and wonder, how fast is this actually? It's a super common puzzle. Recursive code can be so clean, so elegant, but figuring out its performance can feel like trying to solve a mystery. Well, today we're putting on our detective hats. We're going to crack that code. So let's dive in.
So this is the big question, right? When a function's runtime depends on smaller versions of itself, you can't just count the lines of code. It's a loop. It's a paradox. To get to the bottom of it, we have to think differently. We have to look for clues.
And this right here is a perfect example. To get the factorial of 4, the function basically says, I'll handle the 4, but I need you to go find the factorial of 3. And that call does the same for 2, and so on until it hits the bottom. This whole process of breaking a big problem into tiny identical pieces, that's the magic of recursion. But it's also what makes analyzing it so darn tricky. All right, so that kicks off our first section, the recursive riddle. We're going to lay the groundwork here and get a handle on the core concepts we need to even begin our investigation. Okay, let's nail down a proper definition here. Just like we saw with the factorial, recursion is all about that divide and conquer mindset. The function is essentially saying, look, I don't know the whole answer right now, but I know how to solve a slightly smaller version of this exact same problem. So I'm just going to ask myself to do that first. Now, to solve any mystery, you've got to speak the language, right? You need a way to describe what you're finding. And that brings us to the language of complexity. And for us, that universal language is big O notation. Now, here's the most important thing to get about big O. We are not trying to calculate the exact runtime in seconds. That's impossible. It changes with every computer. Instead, big O gives us a way to talk about how the runtime scales or grows as the size of our input gets bigger and bigger. And here you can see the whole spectrum, kind of like different speed limits for algorithms. Some are O of 1, or constant time. They take the same amount of time no matter what. Others are linear, scaling up nicely with the input. And then you get to the scary ones, like exponential, which, well, they get very slow, very, very fast. And this is why we care so much. Just look at this. For an input of 100 items, a linear algorithm, O of n, takes about 100 steps. Makes sense. But a quadratic one, O of n squared, whoa, we're already at 10,000 steps. And as that input number grows, that gap becomes absolutely astronomical. Knowing the big O is critical. Okay, we've got our lingo down. Now it's time to find the smoking gun. Every recursive algorithm leaves behind a very specific piece of evidence, a mathematical formula, that is the key to the whole case. And this is it. This is our big clue, this fingerprint. It's what unlocks the entire mystery of the algorithm's complexity. If we can just find it and solve it, we've cracked the case. So what is this thing really? Well, a recurrence relation, which we usually write as T of n, is just an equation. It breaks down the total time into two simple parts. First, the work the function does right now, and second, the time it takes to do all the smaller recursive calls it makes. It's a perfect little mathematical model of our code. So, we have our clue, the recurrence relation. But a clue's no good if you don't know what to do with it, right? So let's open up our detective's toolkit and check out the methods we have for actually solving these things. For this investigation, we've got 3 main tools at our disposal. There's the substitution method, which is kind of like a guess and prove technique. Then there's the recursion tree method, which is super visual. And finally, the master theorem, which is, well, it's our ultimate shortcut. First up, the substitution method. This one requires a bit of intuition, almost like you're a psychic. You have to make an educated guess about what you think the big O complexity is. Then, you use a formal proof to show that, yep, your guess was right all along. It's super rigorous, but it all hinges on making a good guess right at the start. But what happens when your function doesn't just call itself once, but twice, or even more times? Things get really complicated really fast. The substitution method can get super messy. We need a way to see all the work being done. And this is where the recursion tree method is an absolute lifesaver. I love this approach because it turns that abstract equation into a concrete picture. Every node in the tree is one function call, and you can literally just add up all the work on each level to find the total. It's an amazing way to keep everything organized. Okay, the tree method is great, it's solid, but it can still be a lot of drawing and adding. Wouldn't it be amazing if for a whole bunch of common problems, there was just a formula you could plug the numbers into, a cheat sheet? Well, you're in luck. It's called the master theorem. And for a very specific but very common type of recurrence, this thing is a game changer. If your algorithm breaks a problem of size n into a smaller problems, each of size n over b, this theorem can just give you the answer. It's an incredibly powerful tool to have. The theorem basically comes down to 3 possible outcomes. It all depends on one comparison. It asks, which costs more? The work you do at the very top of the tree to split the problem up, or the total work done by all those tiny little base cases at the very bottom? In case 1, the work at the bottom, at the leaves, dominates. In case 3, the work at the top, at the root, is the heaviest part. And case 2 is that perfectly balanced scenario where the work is spread pretty evenly all the way down. It's like a recipe that gives you the right answer every time. So, let's bring it all together. We've gathered our clues, we've used our tools, and now it's time to talk about why this whole detective story really matters for anyone who writes code.
Because let's be real, this isn't just some abstract theory for a computer science class. Understanding the complexity of your own algorithms is what lets you write code that doesn't just work, but works well. It's how you build systems that don't fall over when the number of users suddenly doubles. This is a practical, essential skill for any serious developer.
And that was our journey. We started with the puzzle of recursion. We learned the language to talk about it, big O. We found that crucial piece of evidence, the recurrence relation, and then we broke out our toolkit with 3 powerful methods to finally solve the case and find the algorithm's true complexity. So there you have it. You've got the framework, you've got the tools. You can now analyze pretty much any recursive algorithm that comes your way. The only question left is, what complex, fascinating problem are you going to solve next? Thanks for joining me.